Let's work together on the review for our exam 1. Let's review first of all the interval notation. The interval notation is required for all the different problems that we will be solving in our class. The practice problems in this PowerPoint presentation are given in these different slides. So, interval notation. The interval notation is following the rules of the line of real numbers. As we can see on the first example right here, if we want to notate the 3,8 interval, we have to start with the number 3, that is the smallest, and the right number will be the number 8, and we have to include these two numbers in parentheses. As we can also see right here, if we want to move on and include, let's say, the number 3, then what we need to change is the parentheses into brackets. So if we include the number 3, then we have to include brackets in front of the 3. If we want to include both 3 and 8, then we put brackets next to 3 and next to 8. While for positive and negative intervals, positive and negative infinity, we want to also always start and end with a parenthesis, because these are not numbers but they are points. So first of all, the definition of a function. A function is a relation where every input has one unique output. When we work with functions, we can identify if a relation is a function either using tables or using graphs. When we use tables, then it is important to focus on the x column. So we don't look at the g of x or the h of x column, but we focus on the x column. If there are no repeated values on the x column, then this means that this is a function. The g of x for this region is a function, although the number 1 and 2 have the same output. This doesn't matter, because each one of these numbers have a unique output. 1 has an output of 2 and 2 has an output of 2. While h of x is not actually a function, and the reason is, looking at the x column, we can see that we have two 4s, meaning the number 4 has two different outputs, 5 and 7. When the function is given to us not in tables but in graphs, then we work with the vertical line test. We should think about having a vertical line that actually shatters the entire function. If at every point that this vertical line, as it moves from left to right, shatters the curve only at one point, then this is a function. And this happens with this parabola. So g of x is a function. While h of x is not. And the reason is, if we repeat here the vertical line test, then we can see that exactly, let's take an example, the vertical line at -3, it crosses the curve in two different points, at -3 and at +3 on the y-axis. So this simply means that we have two outputs for the same input, the input -3. So this makes it not a function. h of x is not a function. let's look more in depth the different functions. So what we will be looking here now are different problems, like for example linear functions. Let's look at a table again for a linear function. How can we recognize that a function is a linear function from a table? We should focus on the f of x, or k of x in this case, column. We should go from step to step, from row to row, and count how many units we increase or we decrease from row to row. So we can see on the x column that we go from number 1 to 2 to 3 to 4 to 5, so units. We go over 1 unit at a time. From 2 to negative 2 we go down 4 units. From negative 2 to negative 6, 4 units. From negative 6 to negative 10, 4 units. From negative 10 to negative 14, 4 units. So overall, what we can see is that we decrease by 4 units at a time. Negative 4 is going to be the slope for this linear function, and yes, it is linear, as long as this step is kept constant. We are working with a linear function. Now if we want to find now what is this linear function, we can look at the table. Now as we move on from 1 to 2, we can also move on from 1 to 0, the previous number. So we have to go up 4 units, so this number would be the number 6. So it would be 0 on the x column and 6 on the k of x column. This would be the y-intercept. So our function is k of x, that is equal to negative 4x plus 6. Now, let's focus on some information that we have about functions. Linear functions, mx plus b, have domain and range that is the same, all real numbers, because we have no reasons to exclude any of those. On the other side, we have quadratic functions. All quadratic functions of the type ax squared plus bx plus c have domain that is from negative infinity to positive infinity. Again, all real numbers. And this holds for all quadratic functions. The same holds for all polynomial functions. Again, what we have are domains from negative infinity to positive infinity. So this holds for all linear, quadratic, and polynomial functions. The same is true for cubic root functions. Cubic root functions, whenever you have a cubic root, or any odd, for that matter, radicand in your root, the domain and the range for these functions is from negative infinity to positive infinity. 3, 5, 7, 9, 11, all of them. Now let's focus on how we exclude some points when we calculate different functions. One case are the square root functions. Anything that is under the square root should be positive. So the domain for square root numbers are all the numbers that are greater or equal to minus b over a if under the root you have a linear function. So in this case we have x plus 5. X plus 5 is under the root. So what we need to do is solve x plus 5 greater or equal to 0. So this means that x must be greater or equal to negative 5. So the domain is from negative 5 to plus infinity, but remember that we have to include the negative 5, so we have bracket on the negative 5. Rational functions. Also, we need to exclude some numbers. And these are the numbers that make the denominator equal to 0. So, in the case that we have a linear function at the denominator, we have to solve it and find the number that makes it 0. 2x plus 4 should be different than 0. In order for this to be different than 0, then x must be different than negative 2. So, we have to exclude from our domain the negative 2. From negative infinity to negative 2, union from negative 2 to positive infinity. What we exclude here is the number -2 with the parentheses. In general, for rational functions, the domain should exclude all the numbers that they make the denominator equal to 0. Right here we can see the different cases for the domains. It's just an explanation, and we can understand what we should do in order to make sure that our domains are, how to find our domains looking at the graph. So when we have a curve like the one that you see here, the linear function, a line, we should try and see as the line moves to positive infinity on the right and negative infinity on the left, the specific one, we can see that all the points on the line, they have some x values that they appear on the entire x-axis. So this simply means that includes all the real numbers. While on the right side you have a rational function, and you have to exclude the number 8 because the number 8 is what makes the denominator 0. This makes the graph quite strange. It splits into two branches and that they diverge from each other in order to exclude the number 0. Now let's focus on ranges, especially ranges for quadratics. When the parabola that you have has a minimum, let's say the one that you see that is at -46, then this is the minimum point that you have. So you focus on the y-axis and you want to see what is the minimum point, the minimum y-coordinate that a point can have for this parabola. And this, of course, is the minimum of the parabola, the -46. So in this case, all the other points have, above the -46, have some y coordinates that they correspond to numbers on the y-axis that are above -46. They are bigger than -46. So the domain is, the range is from -46 to +infinity. When you have a maximum on your parabola, the same thing happens, but the domain now, the range now is from -infinity to +46. In the specific PowerPoint slide, we can see that we have a mistake because the 46, next to 46, we should have a bracket. The 46 on the right side and the -46 on the left side, they should be included in the range. So we should have a bracket. Pay attention to that because there is a typo on the slide. Now, let's see piecewise functions. What we want is to see how we can graph a piecewise function given the rule. The first step that we need to focus on are the restrictions. We take all the numbers out of the restrictions. Here we have the number 2 and the number 3. We consider those numbers and we graph the vertical lines that pass through the points 2 and 3. So x equals 2 and x equals 3. These are the two vertical lines that they will split the entire Cartesian plane into three areas actually, the ones that you see right here. Each one of those areas will correspond to one of the three branches on our function when we graph them. And they will go from left to right as we go from top to bottom on the branches. Then we start graphing each one of these rules, each one of these functions, and start with x plus 3. This is a linear function. In order to graph it, we need 2 points. We need to find those 2 points and graph them on our graph. Now, remember that you should always find the points that correspond to the restrictions. So you definitely want to graph the points at x equals to 2 and x equals to 3. So let's see. The green line that you see corresponds to x plus 3. You can find 2 points any 2 points, including the number 2, because 2 is the number where the red vertical line shows you that the green line will stop, the x plus 3 will stop. So you really need to find the corresponding point for number 2. 2 plus 3 is equal to 5. So when the x is 2, the x plus 3 will be equal to 5. So the point, the corresponding point, will be 2, 5. Then you are going to work on the middle section of your graph and you will graph the parabola. For the parabola, you need more than 2 points. Definitely you want the point for x equals 2 and x equals 3 because these are the 2 ending points for the parabola, but you also want an intermediate point to calculate and find the f of x in order to graph it properly. And this gives us this purple that doesn't show very well, but it is a curve. So you will calculate the point for f of x equals to 2 and f of x equals to 3. After you finish the green line and the purple line, you are going to also graph the horizontal line that corresponds to the last branch. Now, note that for that one, all the points have the same y coordinate. And this is going to be equal to 10. That's why the line is horizontal. Again, what you need to pay attention is not only how to graph the different branches, but how to graph the points where we have the change between the branches. So here the point 2, 5 and 3, 10. These are the important points that you definitely want to calculate and make sure that you know if you should include in your graph or leave it open. Three, 10 is the point that you can get it from the third branch. 2, 5 is the point that you get from the first branch. Why from the first branch? Because you have the equality, so you want the x to be equal to 2, and if x is equal to 2, then the f of x is calculated from the first branch. So it's going to be 2 plus 3 equals to 5. While the other point is calculated by the second branch of the equation. Why? Because the equality now is at 3, at x is less or equal to 3 on the second branch. So if you plug in the 3 inside the second branch, then you have 3 squared plus 1 that is equal to 10. And that's why the 3, 10 point should also be included in your graph. Now, one thing that you need to remember is that in the previous example that we had an equality on the second branch. While here I'm giving you an example where we don't have this equality. We have less than 3 on the second branch and greater than 3 on the third branch. So the number 3 is not included in any of the branches. Although you need to calculate the f of 3 for those two in order to see exactly where the graphs of the third branch and the second branch end and start, we need to leave this point open and show it with an open circle. Now, what should we do if we want to start with a graph and understand what is the piecewise function, the rule of the function, if we have the graph. In this case, we have two branches. How do we know? We have two different equations, two different lines. And also these lines, as you can see, they don't connect. Although the one stops, the green one stops at when x is equal to 2, the purple one starts where x equals to 1 actually. What we also see is that the green includes the point x equals to 1, while the purple one doesn't include that point. So what we need to do is to actually find the equations of those lines. But the first thing that we do is we graph a vertical line that passes through the number 1. That is the point where the two lines are separated. So we graph this line in order to remember that what are the different points that we need to calculate and what are our restrictions. The first thing that we write are our restrictions. X less or equal to 1 for the first branch, for the green line, and x greater than 1 for the purple line. Why less or equal to 1 for the green line? Because the point is included. You see it and it's shaded. While in the purple line, this point is not shaded. It is open. Now we graph the line. We just need 2 points. So I consider the point 1, 4 and 0, 3. These are the points that they will give me the slope, and also 0, 3 gives me the y-intercept. In the same way, I will continue and find the purple line. But let's do this one step at a time. Let's find the rules now. For the green line, we can see that the rule is equal to x plus 3. Why? Because 4 minus, if I want to find the slope, then I have from the 2 points 1, 4 and 0, 3, I will have to subtract 4 minus 3 and 1 minus 0 in order to find the slope. And I have the intercept. For the extrema, I want to remind you that we have two types of extrema: global, absolute, and local. In this specific example, I have no absolute extrema because the lines, the curves, increase in both sides, while I do have a local minimum. I don't have a global maximum, I mean, because they increase on that side, while I have a local maximum and a local minimum at these 2 points. I also have an absolute maximum because the curve increases from both sides. Let's see an example. This function that we see has no absolute minimum or maximum, and the reason is that it starts from positive infinity and it goes down to negative infinity on the right side. So, no absolute minimum or maximum. Although this function has local maximums and local minimums. This is the local maximum and it is at 18.503, 67419. So the local maximum will be the number 67.419, while the corresponding x for the maximum is 18.503. The local minimum is at negative 7.836, negative 23.951. And you can see it right here. The minimum is the number negative 23.951, while the corresponding x for the minimum is negative 7.836. If we want now to find where the function is increasing and decreasing, we should focus on the maximum, local maximum, and the local minimum. We know that as the curve approaches from the left the local minimum, the curve is decreasing. And as the curve leaves the local maximum from the right to the right, then it's decreasing again. That's why the decreasing intervals that correspond to this curve is from negative infinity up to the x-coordinate of the vertex that I see right here, the local maximum, and is negative 7.836. And also, it starts from 18.503, that is the x-coordinate of the local maximum, and it goes to plus infinity. If I want now to see where my function is increasing, I need again to focus on the local maximum and local minimum. But I know that as I leave from the local minimum from to the right, then the function increases. And increases, as you can see, up to the local maximum, where it will start decreasing again. So this is where the curve is increasing. Now the corresponding axis, the x-interval where the curve is increasing, is the blue interval that you see here, that again it starts from negative 7.836 and it goes up to 18.503, the x-coordinates of the local minimum and the local maximum. Let's assume now that we want to find for what values of x the f of x is less or equal to 0. In order to do that, we need to focus on the x-axis, since the x-axis is where the f of x is equal to 0. So, we focus on the x-axis and under that. Why? Because the f of x is nothing else than y. So we focus on the y-axis and we try to find on the y-axis which values are negative. Negative are all the values, or equal to 0, are all the values from the x-axis and down. So this is the part of our graph that we should focus on. Again, f of x is the same thing as y. That's why we focus on the y-axis, right here. Now, after we determine which part of the Cartesian plane we want to focus, less or equal to 0, x and under. What we need to do is say what part of our curve is under that line. So it would be a good idea to shade the part of the curve that is under that line. The part of the curve that is under the line is from negative 20 to 0, and then from 25 to positive infinity. If you look at these areas right there, now you should see that each one of the points of this part of the curve has a negative y. This is what shows us. Take any point there, they will correspond to a negative y. Okay, now what we want to do is to understand what are the x's, not the y's. We know the y's. The y's are from 0 to negative infinity, down, if you take your curve. But what we want is to see for what x intervals this happens. Well, as you can see right there, the intervals that corresponds into that will be from negative 15 to 1. It is not clear here that the second x-intercept from the left is at positive 1. The dot seems to be exactly at 0, but it's not at 0. It's a little bit right of 0. So from negative infinity to 1, is the first interval, and from 30 to positive infinity is the second interval. So, first you find which part or up or down area of the Cartesian plate you want to focus. After you do that, you shade the curve in order to see which part of the curve you focus on, and then you correspond the intervals on the x-axis that correspond to that part of the curve. This is how you find the x intervals, the x values for which the f of x is less or equal to 0. Now for this problem right here, we can see that it has x-intercepts are at negative 1.286, 0, at 1, 0, and 1,899, 0. These are the x-intercepts. The y-intercept now is going to be at 0,2. We can see it where the red curve crosses the y-axis. The specific curve also has a local maximum and a local minimum. The local maximum appears at the negative 0.766, 2,291, and the local minimum appears at 1.566, negative 2.277. The domain of the following function is going to be from negative infinity to positive infinity as the function increases all the way to the positive infinity, and it starts from negative infinity. If now I want to find the intervals where the f of x is increasing or decreasing, then again, remember what I need to do is to find for the intervals that is increasing from the left of the local point, of the local maximum to the local maximum, and from the local minimum to the right. And the intervals that I get are from negative infinity to negative 1.286, and from 1,0.899 to plus infinity. These are going to be my increasing intervals. The decreasing intervals will be from the point from the local maximum to the local minimum, from negative 0.766 to 1.566. And you can see right here where your function is decreasing. And of course the corresponding x interval for this function from the x-coordinate of the local maximum to the x-coordinate of the local minimum. Continue please with these problems, try to solve them, and if you have any questions let me know. Now to find the average rate of a curve between 2 points, the problem is solved for you, and don't forget also to remember the net change and the formula for the net change. Let's look now at the definition of one-to-one function. The one-to-one functions are the functions that for every output there is one unique input. Again, to identify those functions, we start with tables. If we have a table, then we focus on the g of x or f of x column, the column where I have my images. If there are repeated values in that column, then this means that the function is not one-to-one. So in this case, the g of x is not one-to-one function because the number 2, is an output that is the same for 1 and 2 inputs. While the k of x, each one of the values on that column are different from each other, so this means that this value is one-to-one. For the graphs, what I need to do is run a horizontal line test similar to the vertical line test. What I want is the horizontal line test to cross the horizontal line to cross the curve only at one point. For the h of x, as you can see, is not a one-to-one function because it crosses it into two different points. Here are different examples and practice problems for one-to-one functions. Let's focus now on inverses of functions. Every point a comma b of a function, if this function has an inverse, can be flipped, and the b comma a point will be a point of the inverse of the function. The domain of f of x is the range of the inverse, and the range of f of x is the domain of the inverse. The two function curves are symmetric always to around the y equals to x line, the bisector of the first quadrant. The table of values of f of x also can be flipped, so remember that if you have calculated values for a function, then if you flip the columns of that table and you put the x in the place of f of x and the f of x in the place of the x, you get points for the inverse. And of course the inverse property that tells us that if you compose the two functions, the result will be x. So right here we can see an example of two functions, x to the third plus 6 and square root or a third root of x minus 6. And we can see that these functions are inverse of each other and they are symmetric around the red line. Now look at the points 0, 6 and 6, 0 on the black curve, negative 1.8, 17, 0 and 0, negative 1.8, 17 on the black curve. You can see that basically each point of the red curve will correspond to a flipped point on the black curve, and the curves are symmetric around the y equals to x line. And here we see another example similar to the one that we had before. The difference here is that the function that we start with, is a quadratic function. Remember that this is a parabola, and parabolas are not one-to-one functions. So if you want to find the inverse of this function, what you need to do is to restrict the parabola. And this is what you see on your screen. So if you want to see the entire parabola that is given by x squared minus 6, then the entire parabola is this that you see on your screen. But we cannot find the inverse of that. As you can see, it's not one-to-one. It doesn't pass the horizontal line test. So what we need right here is to restrict the domain of this function from negative infinity to positive infinity and restrict it to half of it. And we take from 0 to positive infinity. Once we restrict the domain, we can inverse this function and get the inverse that is going to be the square root of x plus 6, the blue curve that you see on your screen. Now if you pay attention to the points, you will see that the points are inverse of each other. And also you can see that the domain of the red line is the range of the square root of x plus 6, while the range of square root of x plus 6 is the domain of x squared minus 6. Now, what are the steps to find an inverse of a function? Let's start with a very simple function that is a linear function to work with. F of x is equal to 3x minus 5. The first step is to change the f of x to y. So we have now y equals to 3x minus 5. The second step is to interchange the x with the y. So for the x I plug in y, and for the y I plug in x. So it's x equals to 3y minus 5. And the third step will be now to solve this equation for y. Okay? This is a linear equation, so it's simply to solve it. The first thing is to pass the negative 5 on the left side, x plus 5 equals to 3y. And then you want to isolate the y, but let's first flip the equation. There's no harm to that in order to see it better. And then you divide both sides of the equation by 3. You cancel the 3's and you have y equals to x plus 5 over 3. This now is the third step. And the next step is to change the y with the notation of the inverse function, f to the negative 1 of x. So change the y with f to the negative 1 of x. And this is equal to x plus 5. So x plus 5 over 3 is going to be the inverse of the initial function. Let's do the same with another function, quadratic now. In order to find this, we first need to remember that we need to restrict the domain of that function. Okay? So it's going to be from 0 right here to plus infinity. The first step is we change the f of x with y. So y equals to 3x squared minus 2. The second step will be to change the x with the y and the y with the x. The third step is going to be to solve for y. So we follow the PEMDAS rules. We move the negative 2 to the right side, x plus 2 equals to 3y squared. We divide by 3 both sides, so we have x plus 2 divided by 3 equals to y squared. And at the next step we take the square root from both sides. So we have square root of x plus 2 over 3 equals to y. Note the domain of this function now because we have a square root, right? Before we find that, we can change the y with the notation, the proper notation for f to the negative 1 of x equals to square root of x plus 2 over 3. Now, what is the domain of this function? The domain of this function, it will be limited because we have a square root. And the quantity under the square root should be positive. X plus 2 over 3 needs to be greater or equal to 0. So x must be greater or equal to negative 2. So the domain of that is negative 2, plus infinity. Remember, the domain of this is going to be the range of the f of x. And the range of the f of x, and the domain of the f of x, that is from 0 to positive infinity, will be the range of the inverse. Another function, this time a cubic function. Now remember that for the cubic functions the domain is all real numbers and the range is all real numbers. Again we follow the same 4 steps. F of x change with y, then change the x and the y, then take the cube from both sides of the equation and solve for y. The answer for this equation will be f to the negative 1 of x equals to x to the third minus 6 over 2. Remember that since the domain of the first, of the initial, is equal to the range of the inverse, the domain and the range for both functions will be all real numbers. How to find points in an inverse if we only have the f of x with tables? We focus on the f of x row or column. Okay, we want to find the inverse of f at 4. So we need to find the number 4 at the f of x row. Then we will find the corresponding x. So we find the 4, and then we go up to find the corresponding x, that is the number 1. This is going to be the f to the negative 1 of 4 equals to 1. Why? Because if we have 1, 4, the point that belongs to f of x, then the number 4, the point 4, 1 will belong to the inverse of the function. So from one we go to the other. In the same way we can find any one of those numbers. Let's say that we work with 1 or with 8. F to the negative 1 of 8 will be 7. Why is that though? Well, if you compose the two functions, you know from the inverse property that the result is 7. So f of the inverse of f of 7 is 7. And why is that? You first calculate the inner function, inverse of f of 7. If you go to the table, this is the 7 that you have to take from the f of x, and you go back to 6. And then you calculate the f of this is equal to 6. So now you calculate the f of 6. Now the f of 6, how do you find it? You go to the table, and from the x equals to 6, you go back to 7. So this is how you get the actual 7. Or you simply apply the inverse property. How to find points in an inverse if we only have a graph of f of x? So, assume that you want to find the inverse of f at 6. What you need to do is find the point where the 6 is a y-intercept. A y-coordinate. So, the point that belongs to this curve with y-coordinate 6 is the point 1, 6. Okay? Remember, if 1, 6 belongs to this curve, then 6, 1 will belong to the inverse. So the f to the negative 1 of 6 is nothing else than the number 1. We can do the same thing if we are looking for the inverse of f at 12. We find the point 2, 12 on the curve. Okay? And we know now that if we take the inverse of the points, we flip the x and the y coordinates, then the 12, 2 will belong to the inverse. And this is what we see right here. The 12, 2 belongs to the black curve, as you see it right here. Okay? So this means that the f to the negative 1 of 12 is equal to 2. Let's remember a little bit the transformations. This is the table of rules for transformations that you need to memorize. So make sure that you memorize all the rules for the transformations for our entire course. How to find the transformation given the rule. So we need to find the series of transformations if we have the formula of the function. Try to start with the reflection. It's not necessary, but it is convenient. Let's look at the following example. We start with f of x to be the absolute value of x. And we want to write down the transformations to get the following function g of x, that is negative absolute value of x plus 4 minus 3. We see that we have a negative sign outside the absolute value. Outside the absolute value. So this means that we have a reflection around the x-axis. The minus is in front of the absolute. Okay, that's the first transformation. The second is that we actually subtract 3 from the function. Okay, if we do that, then this means that we have a vertical shift, so we shift down 3. And then we see that we add 4 inside the absolute value. So this means that we actually shift to the left 4 units. Let's see its transformation separately. So the red one that you see right here is the function that you get if you take the blue curve for the absolute value, the initial function that we have, the f of x, and we reflect this around the x-axis. It's easy to find an exact graph for the absolute values because you can see the values are easy, the points of each one of those curves are easy to be found. So the first is the reflection. We did the reflection. The next is to shift down. Let's do it with green. So we shift down the vertex of the absolute value 3 units, as you can see. And now you connect the other points that you shift down. And here you have the second transformation. Then you want to take the vertex of the green and move it to the left 4 points. So if you do that, you're going to go 4 points to the left. Let's do it with the blue. Actually, let's do it with purple color. So we move the vertex to the left 4 units. You can count 1, 2, 3, 4. And this is the point where the vertex will appear. You can do the same with each one of the points of the green line. So if you take now that point right there that is at negative 1, negative 4, it's going to move here. And if you take now this point and that point on the line where we have the negative 5, we get those points, and this is our final curve. The curve that you see right here is the g of x. And we get this g of x if we apply these 3 transformations in this sequence, as you can see right here, from the initial function that it was the blue function and it was the f of x. Let's do the same now, but now the transformation is given with a graph. So we have a graph with the transformation and we want to find the actual rule. We start with the parabola, the purple parabola, and this is the x squared. And we want to understand how we get the green parabola with transformations. First of all, you can see that the parabola, the x squared, opens up, while the green opens down. So this means that we have a reflection around the x-axis. So you take the x squared and you add a minus sign in front of it to denote the reflection. Then you can see that the green parabola has been pushed up 5 units. So you add 5 to the negative x squared. Then you can see that the green parabola also has been pushed to the right 2 units. So this means a horizontal shift, so you subtract 2 from inside the argument. Your function is negative x minus 2 squared plus 5. So right here I'm giving you several examples for combinations and domains, composition of functions that you can do and you can observe and review yourself as you study for your work, for your exam. And together we can do some minimal examples, like for example how we combine 2 functions. First of all, how do we find f of 2? F of 2 we just focus on 2. We plug in the number 2 in your function and you have 3 times 2 plus 9 is going to be 15. The domain of this function, and let's say g of negative 2, you plug in the negative 2 here, so you have 3 times 4, it's 6 minus 11, 3 times 4 is 12, minus 11 is 1. How do we combine now the f and g? F plus g, how do we combine them? You just add them up. And if you add up those functions, those two functions, basically what you do is an algebraic addition. You find the like terms, you simplify if there are like terms, and you end up with a polynomial, an algebraic expression, that is, in this case, 3x squared plus 3x minus 2. The domain now of this function is equal to all real numbers, because the domain of f and the domain of g is all real numbers, and you just add them. This is not the case, though, if you work with a division. So if you have f divided by g, then you need to consider that g goes to the denominator. In this case, you have to exclude the values that make g of x equals to 0. So you have to solve 3x squared minus 11 equals to 0. And this will exclude the values plus or minus square root of 11 over 3. Let's practice some more with some composition now. So what we want to do is calculate the f of g of x and the g of f of x right here for these two problems. First of all, f of x and g of x have domains that are all real numbers, because the one is linear and the other is quadratic. So I don't have to worry about domains. The domain of the composition will be all real numbers in this case, because I compose a linear and a quadratic function. F of g of x, the first thing that I need to do is to plug in the g of x in as an argument to the f right here. So f of g of x is the same as f of 3x squared. Now I will apply the f to the 3x squared, so I will plug in the 3x squared in the place of x. And it will be negative 2 times 3x squared plus 6. Now we can simplify that to negative 6x squared plus 6. We cannot do anything else. That's the final answer for this composition of functions. Now we are going to work with g of f of x. So again we start with the innermost function, we plug in the innermost function into the g, and we have g of negative 2x plus 6. And now we are going to plug in the negative 2x plus 6 into the g. So I will have 3 times negative 2x plus 6 squared. I can go ahead now and work with this function because I have a square. One thing that you need to remember is that you cannot distribute the 2 inside the parentheses. This is not allowed. There is no rule that allows us to do that. So what you can do is FOIL. Let's FOIL those two functions. You can keep the 3 outside for now, and you have negative 2x times negative 2x is 4x squared minus 12x minus 12x, if I multiply the negative 2x with the 6 on the right parenthesis, plus 36. I can combine the negative 12x with the negative 12x and get negative 24x. So now I have 4x squared minus 24x plus 36 multiplied by 3. I distribute the 3 and I have 12x squared minus 72x plus 108. As you can see, this is the result for g of f of x, while negative 6x squared plus 6 is the result for f of g of x. And these two functions are completely different. Now, let's compute the g of inverse of g of x. In order to do that, we need to remember the inverse property. We don't need to do anything specific. It's that simple. We focus on the inverse property. G of g to the negative 1 of x is nothing else than x. The same holds for f of negative 1 of x. Again, this is equal to x. And the same property holds for g of g to the negative 1 of 2. This is equal to 2. It doesn't matter what number you put inside the composition of two inverse functions. The result will be the number, the argument that you have in the composition. So g of g to the negative 1 of x is simply x. This is also x. This is equal to 2. And the last one is equal to pi. Okay, let's practice a little bit more again with the function h of x, and let's find for this function the inverse function. I have a third root function, a cube root function, 2x minus 6. The domain for this function is negative infinity to positive infinity. This is equal to h of x. I change the h of x to y in my first step, equals to third root of 2x minus 6. Then I go to the next step, that is 2, and I interchange x and y. X is equal to third root of 2y minus 6. Then I try to solve for y. To do that, I have to take the third power from both sides. When I do that, what happens is that I'm able to cancel the third root with the third power on the right side. I cancel those two, so I get rid of the root. And I have x to the third equal to 2y minus 6. Now I have to solve this for y. I need to isolate the y. With PEMDAS, I move the 6 to the right side as plus 6 equals to 2y. And I divide both sides by 2. In this way, I have y equals to x to the third plus 6 over 2. And I change now the y with the function that is the inverse of h, the proper notation for the inverse of h to the negative 1 of x. That's my answer. This is my final answer. And the domain of both the h of x and the inverse of h of x are the same, all real numbers. For factoring, I'm not going to go through every step. I have different examples and step-by-step instructions on how to solve different problems here using all the methods. The special identities are important. I want you to memorize them, especially the first one, the second one, and the fifth one for this exam. But as we move on with the class, we need to make sure that we memorize each one of those because you should be able to use them. Let's work with the last problem. The first two, please do them and let me know if you have questions. The last one is a little bit strange. I have x to the fourth minus 16y to the fourth, and I don't have any specific identity for this. Nevertheless, I need to realize that x to the fourth can be written as x squared squared. So I can split the 4 as square to 2, 2 to the 2. Because as we know, if you have a power to a power, you multiply the exponents, and the result is the product. So I have x squared squared and 2 to the fourth y to the fourth. I can rewrite this as x squared squared minus 2y to the fourth. But this can be split as 2y to the second to the second. And now I have a difference of squares. I write this as a difference of squares, so I split it down to x squared minus 2y squared and x squared plus 2y squared, using the difference of squares. What I want you to see now is that although this cannot be changed, the sum cannot be changed to anything, the left side, that is x squared minus 2y squared, is a difference of squares. And because it's a difference of squares, I can split it further to x minus 2y times x plus 2y. Times x squared plus 4y squared. And this is my final answer. So we want now to graph the parabola that is given in this slide, 4x squared minus 11x minus 3. The first step is to rewrite the coefficients. So we want to make sure what is the a, what is the b, and what is the c. A is equal to 4, b is equal to negative 11, and c is equal to negative 3. In order to graph a parabola, I need 5 components. I need to identify the 5 components of this parabola. And the 5 components are nothing else than the extrema, the y-intercept, the x-intercept, the vertex, and the line of symmetry. First of all, we are going to work with the extrema of our function. When the a is positive, then this means that the parabola opens up. When the a is negative, then this means that the parabola opens down. In this case, a is equal to 4. That is greater than 0. So this means that it opens up. It has a minimum. If it was negative, then it would have a maximum, as it will open down. So this is the first important thing that we need to remember. Give me a moment here because I have a technical difficulty. the next step that we have to look at is the y-intercept. The y-intercept for a parabola is always the constant. That is, in this case, the -3. Just remember to take the negative sign along with the number. So if you want to write this in point notation, then you have to write 0, -3, because -3 will be the y coordinate. The next step is to calculate the x-intercepts. The x-intercepts for this parabola will be calculated if we set the trinomial equal to 0. So you set f of x equals to 0, and this holds for all the functions. When you want to find x-intercepts, you set it equal to 0. And you, for this specific one, what you need to do is find the roots of that. You can find the roots either using the quadratic formula or by factoring. And this is what I did here. By solving by factoring, right here, I have x minus 3 times 4x plus 1. So the roots of that will be x equals to 3. Either the first factor will be equal to 0, or x equals to -1/4. The second factor will be equal to 0. And this gives me the two x-intercepts, 3, 0 and -1/4, 0. So I have the x-intercepts, the y-intercept, and I know that the parabola that I have right here has a minimum. So the next step is to find the vertex and the line of symmetry. To find the vertex is simple but tedious, because you need to be very careful with your calculations. The vertex is always -b over 2a, f of -b over 2a. That's the point of the vertex, and it's always like that. Okay? To calculate that for our parabola, since b is equal to -11 and a is equal to 4, we are going to get 11 over 4. This is the x-coordinate. Now you are going to take this x-coordinate, 11/8, and you will plug it in to the f. That is 4 times x squared minus 11x minus 3. So you plug in the 11/8 there, and you do the calculations for that. And if you do the calculations for that, then the result that you get is -10,563. So you take the x-coordinate that you found easily by -b over 2a, and you plug it into the function to calculate it for the specific number. As you can see, you may have to deal with fractions. Now, for this presentation, we want to do it really fast, so the answer is -10.563. But if something like this is given, you really need to go through the steps and calculate the fractions and get your final answer. The vertex for this parabola is 11/8, -10.563. The line of symmetry of the parabola, where the parabola is symmetrical around a vertical axis, the vertical axis is going to be x equals to 11/8. So it's going to be always x equals to -b over 2a. So now I have the vertex, the x-intercepts, the y-intercept, and I know that the parabola opens up. And I'm ready to actually graph the parabola. As you can see right here, we have the x-intercepts, -0.25, that is 1/4, -1/4, 0, 3, 0, the y-intercept, 0, -3, and the vertex, 1.375, that is nothing else than 11/8, -10.563. And I'm ready to graph it. The parabola opens up, and the line of symmetry is equal to x equals to 11/8 or x equals to 1.375. Let's look at some problems together now. These are the problems that we solved together, problem 1, 2, 3, and 4. For each one of those I have written extra explanation for you, so you can read the explanations. Let's move on to problem 5. What we want is to calculate the f of x and the domain, the f of g of x and its domain, the g of h of x and its domain, and to find the inverse of k. When we start to do the composition of f of x, we always start from the innermost function. And because we focus on the innermost function, we also need to find the domain of the innermost function. So for problem A, the domain of f of x is all the numbers but 0, because 0 makes the denominator 0. Now, f of x, what I need to do is plug in the 1 over x, that is equal to f of x, inside my parentheses, and then apply the f of 1 over x. You can see right here that I'm getting a mixed fraction, that is 1 over x. And this is nothing else than 1 times x over 1. The reason for that, of course, is that when I have two fractions or a number divided by a fraction, what I need to do is to actually multiply the number by the reciprocal of that fraction. So we are looking now at the solution of A, and the result is x. Well, if you look at the number x, the function, the composition of functions gives you equal to x. The domain of x is all real numbers. But since in order to get this x, you had to put the 1 over x at the denominator, then this means that you should consider the domain of that function. So your final domain will be restricted by the domain of f of x, that is the inner function. Your final domain for each one of the compositions will be restricted by the inner function, by the domain of the inner function. So the domain of f of x is all real numbers but 0. And this is important to remember. When you compose functions, the final domain doesn't matter what the function look like when you finish with the composition. The domain of that function will be restricted also, so you have to exclude also the values that you exclude for the innermost function. And this is very important to remember. Again, the reason is that when I compose the f with the f of x, I don't suddenly, immediately get the x. What I do is that I go through the steps of 1 over x. I have this in my equation as well. So this means that I have to exclude the number 0 because it makes the 1 over x right here equals to 0. Equals to undefined. So I need to exclude the number 0 from the final domain. Now, in the same way, I will work the number b. And I will have right here, in the same way that I had for the a, the x, but the domain of the x is all real numbers but 0 because the x appeared at the denominator. In the same way, I will work the second problem. So now, for problem B, what I do is I have to compose the f with a g of x. The g of x is going to be the function that is the innermost function to my composition, f of g of x. So I focus now on the g of x, that is the innermost function, 1 over x squared. And I need to find the domain for this function. All real numbers, but the number 0. Okay, this is the domain that you see written right here. Then what I do is I take the composition, f of g of x, and I plug in the g of x, that is 1 over x squared, inside the f of x. And then I apply the function f of x to that, and I have 1 over x squared. I take the reciprocal and I multiply, and my result is x squared. Again, this is a quadratic function. As a quadratic function, the domain of that is all real numbers. But since I have used the x squared at the denominator in an intermediate step, I need to exclude the number 0 from my domain. So I restrict my final domain to the domain of the innermost function. Now let's look at the last one, g of h of x. Well, the h of x is nothing else than a linear function, x minus 3. Because it's x minus 3, the domain is all real numbers. When I do the composition, the h of x is the innermost function. So I plug in the x minus 3 inside the g, and now I apply the g, meaning I replace the x square with the x minus 3 square. Now, what I have right here is a slight typo in my slide. I'm sorry for that. I moved on. Just a moment. What I want you to see is that there is a slight typo. Let me fix this for a moment. Some technical difficulties here. So what we need to do right here is to consider what will be the domain of g of h of x. Now, the domain of g of h of x will be all numbers but the one that makes the denominator 0. And the one that makes the denominator 0 right here is the number 3. So, I have to exclude the number 3 from my domain. And the domain is all real numbers but 3. Negative infinity to 3 and 3 to positive infinity. Now, since it's a composition of functions, I need to restrict the domain to the domain of the innermost function. But as you can see, the innermost function is a linear function, so the domain, the initial domain that I had, was all real numbers. So there is nothing that I need to restrict to that. So this means, basically, that the domain of the composition will be all real numbers but 3. Let's calculate the inverse of k, of x. This is a cubic root. I have 7 minus 4x. I need to change the k of x to y equals to the third root of 7 minus 4x. I interchange y and x, so I have x equals to the third root of 7 minus 4y. I take the third power from both sides in order to cancel the third root. X to the third equals to 7 minus 4y, because I cancel this way the third root with the third power. I push the 7 to the left side, x to the third minus 7 equals to negative 4y. And now I will divide by negative 4 both sides of the equation. And this is equal to y. I change the y with k to the negative x, that is the proper notation. And this is equal to negative x to the third plus 7 over 4. That's the final answer. Okay, let's work with another quadratic function here. Actually, let's work this problem right here. F of x equals to 2 plus square root of x plus 3. We want to find the domain and the range of f. We want to find the specific points and graph them on our paper, and then sketch the graph of x. So the first thing that we are going to do is find the domain. The domain is all numbers such that x plus 3 is greater or equal to 0, since this is under the square root. So we're taking all numbers that are greater than negative 3, from negative 3 to positive infinity. That's the domain of the function. Okay, now we are going to leave the range for the function to find it after we graph the function. Let's find now the points. And I have the following points here. X, negative 3, x equals to negative 2, 0, and 6. If I plug in the negative 3 in the square root, I get 0, so f of x is 2. If I plug in the negative 2, then square root is negative 2 plus 3 is 1, plus 2 is equal to 3. If I plug in the 3, then I have 2 plus square root of 3. And if I plug in the 6 inside the square root, I get square root of 9, that is equal to 3, plus 2 is equal to 5. Now, I graph the points. Negative 3, 2, negative 2, 3, 0, 2 plus square root of 3, and 6, 5. Now 2 plus square root of 3 is 3, 4, something like that. So I will approximate it on my graph. I connect the points. For the moment, I don't want you to extend the line, the curve, anywhere. Just connect the points that you have right there. Now you can see that on the left side, on the vertical line is the end of my domain. So I cannot extend the specific line further than this vertical line that passes through the negative 3. Be careful with that and make sure that when you graph your equation, you graph it from -3 to positive infinity. Do not extend your curve further than what the domain says. Now, if you look at this curve, you also see what is the range, because the range is from 2 and up. You can see the range on the y-axis. The minimum point that I have right here is the point -3,2. So this means that the range starts from 2 to the positive infinity. So you do have your range at this point. But if you want to verify it, what you can do is graph the inverse function and then calculate the range, because it's also easier. So two ways to do it. Either you actually find the graph of the inverse function first and then calculate the range. So you find the inverse function, you find the domain of the inverse function that will be the range of this, and then you write it down. Or you just see the graph right here and you see that your minimum for the curve is at -3,2. So 2 is your minimum on the y-axis. So the range is from 2 to positive infinity. Now, what I can do right here is I want to graph also the points of the inverse. This is something that I want to do. I don't need to calculate the inverse function to graph the points of the inverse. I already have the points of the inverse. And remember that. So instead of going on and trying to solve what is the domain and the range of the inverse, and what is the formula of the inverse, what I can do is go and graph it first, because they will definitely ask me to graph it. How do I graph that? I take the table of values for f of x that I have on the left of my screen, and what I do is I flip the columns, because we said every point of f of x, if you flip the x and the y coordinates, will give you a point of the inverse. So now I'm going to make the table of values for the inverse. That is going to be 2, -3, 3, -2, 2 plus square root of 3, 0, and 5, 6. I just flipped the points. At the next step, I graph these points. It's easier to work with a graph. That's why I asked you to follow these steps. So find the points, graph them on your graph, as we do right here. 2 plus square root of 3 is 3 point something and 0, right there. And then the next point is the 5, 6. That is somewhere above my line, right there, since the number 6 is right here. Then the next step that you have to do is connect those points. Again, don't extend, just connect them where they are. Now, you see me graph this line that passes through the bottom point. The reason for that is the following. I know that my graph cannot extend further down than this point. Why? Because the point 2, -3 corresponds to the point -3,2 of the f of x. So as the vertical line that you have is the vertical line that determines the domain of f of x, the horizontal dotted line that you see is the line that determines the range of f of -1 of x. So I know that my line stops right there and increases to the infinity on the top side. It's obvious right here that these lines are symmetric around the y equals to x. So now I'm ready to calculate my domain and range of each one of the functions. Okay? Now, the domain of the initial function is from -3 to plus infinity. So this means that the range of the inverse will be from -3 to plus infinity. I know that for most of the students it's easier to see the domain. Now, if you look at your inverse function, the domain starts from 2 and it goes to positive infinity, right? From 2 to positive infinity. This is going to be the range for the initial function, since the range and the domains flip between those functions. So I can write down the range of f of x, that is 2 to positive infinity. So now I have domain and ranges, I have the tables, I have the graphs. And I still do not have the sketch. I know that the sketch is a little bit difficult to do, but you can definitely write and solve for every other part of the question until you reach the point to write a formula for the inverse function. Let's do the inverse function now together. F of x equals to 2 plus square root of x plus 3. In order to find that, in order to find the inverse, what we need to do is, step 1, change the f of x with y. So now you have y equals to 2 plus square root of x plus 3. Then exchange x and y's, and you have x equals to 2 plus square root of y plus 3. Then you move the 2 to the left side. Again, you move first the 2 because you cannot deal with the square root yet. You need to focus and get rid of everything around the square root to continue. Because your goal is to get rid of everything and isolate the y. So you move the 2 to the left and you have x minus 2 equals to square root of y plus 3. And now you take the square from both sides to get rid of the square root. And you have x minus 2 squared equals to y plus 3. You move the 3 on the left side, and that's your final answer. So you replace y equals to f to the negative 1 of x, and you are done. Okay, let's do problem 8 together, and this is an easy one. We want to look at each one of those tables and find which one of those is a function, if any of those, which one is a linear function, and calculate some composition of functions. So let's start with the first one. To see if it's a function, we focus on the first column, on the x column. And what we want to see is if there are repeated values. There are no repeated values, so this means that every x corresponds to a single y, to a unique output. So this means that this is a function. The next step is to see if this is actually a linear function. Again, to see if it's a linear function, we want to go from step to step, from row to row, and see if we keep the same pace. So from 1 to 0, we go down 1. From 0 to 1, we go up 1. From 1 to 4, we go up 3. So, minus 1 plus 1 plus 3. Not a linear function. We don't have a constant pace, so we don't have a constant average rate. Not linear. Then, we want to calculate the f of 3. To do that, basically, we find the 3 on the x column, and this corresponds to 9. So the answer is 9. Let's look now at the f of 2. To solve that, we focus on the innermost. What is f of 2? Well, the 2 corresponds to the number 4. So we replace the inside argument of f with 4, and now we calculate the f of 4. that is equal to 60. And that's our final answer. Now the next question is f of g of 1. So we need to work with both tables in order to answer that. Let me clean up my table just a little bit. So, f of g of 1. The innermost is the g. So I want to find first of all the g of 1. 1 corresponds to 2. So g of 1 is equal to 2. So this means that I replace the g of 1 with 2. And I want now to calculate the f of 2. 2, you go to the first table, corresponds to 4. So f of 2 is equal to 4, and that's my final answer. Let's look now at the function g of x, and let's decide if this is a function. Well, again, on the x column, I don't have any repeated values. Negative 1, 0, 1, 2, 3, 4, good. So this is a function. Now, is this a linear function? So from negative 4 to negative 1 is 3. From negative 1 to 2 is 3. From 2 to 5 is 3. From 5 to 8 is 3. From 8 to 11 is 3. Check all of them. If all of them are the same and constant, like here, then this means that this is a linear function and the slope of this function is 3. Let's calculate now the number d. G of f of 1. The innermost function is f of 1. F of 1 from the first table gives me 1. So I replace f of 1 with 1 and I get g of 1 now. So I replace the f of 1 inside the g function with 1. G of 1 is equal to 2. G of 1 is equal to 2 because I look at the right table. Now, what about the inverse of g of 8? This means that I have to go to the g table, look at the column of g of x, because I don't have the inverse of g, find the number 8, and go from the 8 to the corresponding input. And the input for this case will be the number 3. So I go backwards, right? Why? Because if the 3,8 is a point of g function, then the 8,3 is a point of the inverse of g function. So this means that g of inverse of 8 will be 3. Okay? Okay, let's solve another one. G of inverse of 2. Again, I have to do the same, I have to take the same process. So I go to the G table and I focus on this column, on the G column, and I find the number 2. That is right there. And I go backwards. The x is 1, so this means that the inverse of g of 2 at the point 2 is equal to 1. And that will be my answer for that. Now, in the same way, you work with the inverse of f at the point 1. Again, you go to the column of f of x, you find the number 1, and you go backwards. The answer is equal to, well, here we have an issue. Why? Because we have two 1s. But if we have two 1s, we don't have a definite answer. The one is negative 1, the other is 1. Which one is the answer? Why this is happening? Well, this is happening because if you look at this table, you can realize that the f of x is not an one-to-one function. It has two outputs for the same input. So this means that there is no inverse for f of x. There is no inverse function for f of x. That's why you are not able to find the answer. Problem 9. Let's write the transformations to get the g of x. Now the f of x is what we start with, and this is the absolute value of x. Okay. First of all, the red curve, that is the absolute value of x, opens up. the blue, that is the g of x, opens down. So this means that I have a reflection around the x-axis. That's the first transformation. The second one, you can see that I have shifted my vertex from the point 0, 0 to 5. I went up 5 units. You can see it because the vertex of blue is at y equals to 5. So I shift up by 5. And now you can also see that I have shifted up my function to the left 2 units. So shift left 2 units. So I have a reflection over the x, I have a vertical shift of 5 units, and I have a horizontal shift of 2 units. Let's try to put all these together into a function step by step. The first one, reflection over the x, means that I have to put a minus sign in front of my absolute value. The second, shift up, this means that I have to add, because it's up, 5 units, 5 to the negative absolute value of x. And now shift left, it means that I have to add the number 2, but inside the absolute value, because I add 2 inside the argument of my function. So it's negative absolute value of x plus 2 plus 5. This is your g of x. Problem 10. I have a local ice cream store that sells ice cream. When the temperature goes up, it sells more ice cream. When the temperature is 85 degrees, they sold 5 cones. The next day, when the temperature went up 5 degrees to 90 degrees, they sold 75 ice cream cones. So, we assume that there is a linear relationship between temperature and sales, and we want to answer the following questions. Before we answer the following questions, I want us to look at the problem. We have 2 types of variables. What? The number of cones that we sell and the temperature. 2 variables. What is extremely important here for us is to know which one of the 2 will be the independent variable, the t or the x variable, the one that appears on the x-axis, and which one will be the one that appears on the y-axis. This is very important to know before you start solving the problem. Well, on the x-axis, on the horizontal axis, you always put the variable that, using your common sense, doesn't depend on the other. I have cones that I sell and temperature. The number of cones that I sell depend on the temperature. The temperature, though, doesn't depend on the ice cream cones. So the temperature goes to the x-axis, to the horizontal axis. And it's always like that. This is how you read the problems. The variable that is independent of anything goes to the horizontal axis. And that's my temperature. Now the variable, ice cream cones, will go to the y-axis, because this is the axis that's remaining. This immediately gives you the idea of how to set up your points, because you need points since you are going to graph a line. Okay, so the variable that goes on the y-axis, we call it dependent variable. The variable that goes on the x-axis, on the horizontal axis, we call it independent variable. In this case, it's not x, it's t, and we're talking about temperature. Okay, so we want to find the rule of the function, right? And we are going to try and find the rule of the function. What I want us to see is, first of all, that the independent variable, the variable that you are writing your function for, is not x, but is t. So everything that you write from now on must be on t. Although we are used to always use x, if they give us a variable to be t, then we have to use t. Let's write now the slope. What is the slope? You have to find 2 points. Temperature, sales of cones. What are the 2 points that you have? The 2 days. The relations that you have for each one of those. 85 degrees, 50 cones. 90 degrees, 75 cones. These are the 2 relations for the 2 separate days that you have. So, 50 and 75 are cones. And this is your dependent variable, your variable that goes to the y-axis. So these are the numbers that you have to subtract at the numerator. So you will put 75 minus 50 divided by 90 minus 85. The result is 25 over 5, that is 5. And of course, this is your average rate of sales. This is your slope for the line that you need to create. Now the next step is to find the y-intercept for this line, because they actually ask us to find what? To find the entire rule of the function. So we have y equals to 5t plus b, and we need to find the b. In order to find the b, we are going to utilize one of the 2 points that you have, either the 85,50 or the 90,75. It doesn't matter which one you choose to utilize. Just take one and plug in the corresponding for y and t in order to find your b. This is what we will have to do right here. So, if you choose the number 85,50, you're going to plug in the 85 at the place of y, because that's your y. 85 is, the 85 will replace the t, and the 50 will replace the y. Why? Because I have 50 cones, that is the dependent variable, the y variable, and 85 degrees, that is the temperature, the independent variable. So my equation becomes 50 equals to 5 times 85 plus b. And I want to solve for b. So I need to do some calculations here. 5 times 85 is going to be equal to 425. I pass the number to the left side, and I have 50 minus 425 equals to b. So this means that the number is negative 375. b is equal to negative 375. So what is my equation? My equation is I of t equals to 5t minus 375. What is the slope of the function? Well, it's 5. What does it represent? It represents the number of cones that we sell more for every degree that the temperature increases. So whenever the temperature increases by 1 degree, we sell 5 more cones. This is what it represents. Now, we also want to calculate how many ice creams we will sell when the temperature is 105 degrees. 105 is the temperature, is the T. So plug in 105 in your equation in order to find the number of cones that this will represent. If you do that, you're going to get 5 times 105 minus 375. Now, if you do the calculation for that, will be 425 minus 375, and 525 minus 375, and the result for that will be equal to 150. What does this mean? This means that when the temperature reaches 105 degrees, the specific store will sell 150, when the temperature reaches 105 degrees, the store will sell 150 ice cream cones. So the next step is to graph this equation. What am I going to graph? I have two different days, 85,50, 90,75, and I also know that 105 degrees correspond to 150 cones. That's another point. So I have three different points here that I need to graph. So let's graph them. The first one is 85. To 50. The next one is 90 to 75. And you can also graph the other point if you want. That is the point 105 to 150. What you need to do now is connect those points, right? And extend your line up to the t-axis, the horizontal axis. And you need to stop right there. And this is the key here. Why do you need to stop? Well, look at the point that you have between 70 and 80. What is this point? 75. This means that at 75 degrees, what is your y? 0. So this means that at 75 degrees, you are going to sell 0 cones. Is there any possibility that you are going to sell less than 0 cones? No. That's the worst day that you can have. To sell 0 cones, to sell no cones at all. You're not going to buy cones. So this means that your line stops right there. And this is what your range is in this case. So from 75 to infinity, or whatever temperature can reach, is your domain. And your range is from 0 to infinity, or whatever number of cones you can sell. But there is no way that you can extend this line further down than the 75 degrees. Because then this means that would correspond to negative cones, and it makes no sense. Okay, now let's solve one more problem here. And the problem is the following. The number of apples produced by each tree in an apple orchard depends on how densely the trees are planted. If n trees are planted on an acre of land, then each tree produces 900 minus 9n apples. The number of apples produced by the acre is an equals to n times 900 minus 9n. Let's read this carefully. An is the number of apples. It is already given in your equation, in your explanation, the instruction of the problem, that n correspond to trees. So the n is the number of trees, the an is the number of apples. And, what is your independent variable here? The trees, right? The trees give the apples. If the dependent is the apples, because the apples come from the trees. Okay, so this means that your x-coordinate will be the n, your y-coordinate will be the an. They ask us how many trees should be planted per acre to obtain the maximum yield of apples. The first thing that I need to do is to expand my equation. This is a quadratic equation. And I know that every quadratic equation gives me a parabola. Now, a parabola has either a maximum or a minimum. In this case, the a is equal to negative 9, so I have a maximum. The vertex gives you a maximum. Now, the vertex is at a specific point that we know how to find. and the vertex gives you an x-coordinate and a y-coordinate. The x-coordinate will be the number of trees, because that's your x, that's your n in this case, while the y-coordinate is the number of apples. What does the question ask you? What is the number of trees to get the maximum number of apples? So basically it asks you, what is the x-coordinate of the vertex? This is what this problem asks you. What is the x-coordinate of the vertex? How many trees, that is the independent variable, the x-coordinate, on your vertex? So we need to find the vertex. How do we find the vertex? Negative b over 2a is the x. F of negative b over 2a is the y. I'm sorry, what did I say? Negative b over 2a is the x. F of negative b over 2a will be the y. They ask us to find the x only. How many trees? They don't care about the apples. But let's find both, just to make sure that we know how to handle this type of problems. Okay, x, number of trees. F, or a, because this is how we name this function, a of negative b over 2a is the number of apples. First of all, the number of trees. What is my b? Well, the b is equal to 900 here. The a is equal to negative 9. I plug in the values in the equation, negative b over 2a, and I have negative 900 divided by 2 times negative 9. I can simplify the negative 9 with the negative 900, and I get 100 at the denominator. 100 divided by 2 is equal to 50. So what is this? Well, it's the x-coordinate. So these are the trees. This is the number of trees that I need to have in order to get the maximum number of apples. So I answered it. That's the answer to this question. Now assume that they also ask us, what is the maximum yield of apples? Let's do that too. So I need basically to find the y-coordinate of the vertex. That is f of 50. I plug in 50 on my equation to find this. 900 times 50 minus 9 times 50 squared. And this is equal to 45,000 minus 50 times 50 is 2,500 times 9. 9 times 2,500 is 22,500. 22,500. So what I have here is to subtract 45,000 minus 22,500. That is half of 45,000. So my final result will be 22,500. And this is our final answer. This is the number of apples that we will get from 50 trees, and that's the maximum number of apples that this orchard can give us. So basically what it says is that for reasons that I'm not qualified to know why, the truth is that if you plant more trees in the orchard, you're not going to get more apples. Now, we can stop the presentation here and we can do some of the rest of the problems together on Wednesday.